Swayam Prabha. Digital India. Educated India.
Now we are coming to another class of random variable called sub-exponential. In big data analytics, sub-exponential random variables are going to be very useful. We will soon see. The concept of sub-Gaussian is restrictive. So what is that? We had Gaussian, we extended to sub-Gaussian. Further analysis tells you even the definition of sub-Gaussian is kind of restrictive. So what is the definition of sub-Gaussian? There exists a parameter sigma greater than 0 such that expected value of lambda times x minus mu, expected value e to the power of lambda times x minus mu is less than or equal to e to the power of minus sigma square lambda square by 2 for all lambda belong to R. Now please understand, lambda belonging to the entire real line, that is the definition of sub-Gaussian, and that is asking too much. We want this inequality to be true for all lambda real numbers. So I would like to be able to relax this condition. Relaxing the condition lambda on lambda gives rise to a new class called sub-exponential random variables. So if we further restrict lambda to a shorter interval instead of the whole interval, we will be able to extend the notion of sub-Gaussian to sub-exponential. So that gives rise to the definition of what is called sub-exponential random variable. A random variable x is said to be sub-exponential with a mean mu. So G, SG and SE. Gaussian is an exponential family because the distribution is a function of the depends on the exponential function. It's an exponential family. Sub-Gaussian, we don't describe the distribution, but we know the moment distribution, the moment generating function is less than or equal to that of a normal random variable where lambda is real, any real number. Now I would like to be able to restrict. So a random variable x is said to be sub-exponential with a mean mu if there exists a non-negative parameters mu and b greater than 0 such that e to the power of expected value of e to the power of lambda x minus mu is less than or equal to e to the power of lambda square gamma square by 2, where absolute value of lambda is less than or equal to 1 by b. So if b, sorry, the whole thing went back. Oh, I don't know what I did. So when b is strictly greater than 0, if b is strictly greater than 0, 1 over b is a finite interval. 1 over b becomes infinite only when b is 0, but that is not allowed here. Therefore, for all finite values of lambda such that the absolute value of lambda is less than or equal to 1 over b, that means I am allowing the parameter lambda not to be any real number, but to be present in some subset of the real line. By setting nu is equal to sigma and b is equal to 0, we see lambda is less than or equal to infinity. That means lambda is real, and hence sub-Gaussian random variable is sub-exponential but not vice versa. So I am now telling you that a new family called sub-exponential is a larger family than sub-Gaussian, because sub-Gaussian can be obtained as a special case. So, when we allow B to be 0, the interval becomes infinite interval, it becomes lambda becomes a real number. So, requiring B to be greater than 0, we are restricting the interval. So, you can readily see sub-exponential is some kind of a generalization of sub-Gaussian. We have already given Gaussian, we have already given examples of sub-Gaussian. Now, we would like to be able to give examples of sub-exponential. ஒரு கொஸ்டின் கேட்கலாமா? எவ்வளோ நேரம் பண்ணியிருக்கோம் இப்போ? After coffee break? 1.5. So 1.5 already we have achieved 3. So I'm going to continue a little bit. Okay? That's okay? Yeah, no. Good. So what is that we need to do? There exists sub-Gaussian random variable, there is not sub-exponential random variable, there is not sub-Gaussian. Some of you may find this treatment to be slightly bit more mathematical, but you will soon see the impact of this high level of mathematics in trying to talk about dimension reduction in big data analytics. We already talked about use of PCA in dimension reduction. So let Z be a normal random variable, standard normal. Let x is equal to Z square. So that is chi square. So if I compute for lambda greater than lambda less than half, e to the power of expected value of e to the power of lambda times x minus 1, that is given by this integral. Again, by simplifying, by perfecting the square, you can show that this integral has this value. Going from here to here is non-trivial. So you have to perfect the square and use the fact that the integral over the probability density function from minus infinity to plus infinity is 1. So you get this. So in this case, the denominator is 1 minus 2 times lambda. So when lambda is greater than half, x is not sub-Gaussian. X is not sub-Gaussian. You can readily see. You can readily see. So what does this mean? This means that there exists sub-exponential variable which are not sub-Gaussian. Which are not sub-Gaussian. So why is this sub-exponential? Because lambda is restricted to be less than half. You can understand the kind of restriction that comes in. So this essentially tells you when lambda is greater than half, x cannot be sub-Gaussian. So the existence of moment generating function near the mean is actually equivalent to the definition of sub-exponential family. Look at that now. That's a very technical way of looking at it. So when do you get sub-exponential random variables? I want to be able to show the existence of moment generating function near the mean. Near the mean means what? It is on both sides of the mean, but not infinite interval, but a finite interval. So colloquially, I'm sorry, not colloquially, intuitively, existence of a moment generating function near the mean is actually equivalent to the definition of sub-exponential family. Sub-exponential family. So how do I verify that? E to the power of minus lambda divided by, look at this now, e to the power of minus lambda, e to the power of minus lambda divided by 1 over 2 lambda. It can be shown this is less than or equal to e to the power of 2 lambda square. That is equal to 4 lambda square by 2 exponential of that. So for lambda is equal to absolute value of lambda is less than or equal to 1/4. This inequality is true. If this inequality is true, we call it, see, look at this now. If this inequality is true, I can identify the parameter nu and b nu is 2 and b is 4, and for lambda less than the absolute value of lambda less than or equal to 1 over b, it is going to be sub-exponential. Go back to the definition of sub-exponential. Look at that now. There exist non-negative parameters nu and b such that if x is the random variable with the mean mu, and if e to the power of expected value of e to the power of lambda x minus mu is less than or equal to e to the power of lambda square nu square by 2, for lambda in less than the absolute value of lambda to be 1 over b. So look at this now. Mu is the mean, so I am talking about x minus mu, the deviation of x between mu, the expected value of exponential lambda times the deviation of x from mu is less than or equal to e to the power of lambda square nu square by 2. That is the definition. So according to that definition, this inequality can be verified. Therefore, this shows that x z is equal to z square, where z is a normal random variable, x is the square of z. X is the square of z means what? X is chi-square distributed. So chi-square distributed random variable is an example of sub-exponential random variable with a parameter 2 and 4, 2 for nu, b is equal to 4. As with sub-Gaussian, the control of the moment generating function, which when combined with a Chernoff yield the derivation, yield the deviation and the concentration inequalities for sub-exponential families. So what is that we are interested in? Now we are interested in the tail bounds for sub-exponential family. As with sub-Gaussian, the control of the moment generating function. Please understand, the whole thing depends on how do we control the moment generating functions, and the idea has its genesis in Chernoff. So what is called the tail probability of sub-exponential distribution? Let x be a sub-exponential random variable with parameters gamma b as parameters, then the probability that x plus mu plus t, what does it mean? X takes a value beyond mu by the value t. For t in between gamma square by b, it is minus t square by 2 sigma square. This looks like sub-Gaussian. For t greater than nu square by b, it is exponential. So sub-Gaussian, this is exponential bound. So for t small, the bound is sub-Gaussian. Look at this now. When t is small, this bound looks like a sub-Gaussian. And for t large, the exponent scales linearly. So the exponent scales quadratically in t and linearly in t, depending on where b is bounded in the neighborhood of origin or d is bounded away from the origin. So by symmetry, if I can do upper deviation, I can do lower deviation. Upper deviation, lower deviation are mutually exclusive. Therefore, the probability that absolute value of x minus mu greater than or equal to t is 2 times e to the power of minus t square by 2 gamma square, 2 nu square, or 2 times e to the power of minus t by 2b, where the same values of the interval comes into play as in 19. I am going to verify this. Assumes centering, that means mu is 0. So we follow Chernoff now, combine the definition of sub-exponential in 17 and Markov. So by Markov, I have x greater than or equal to t is given by probability e to the power of lambda x is greater than or equal to e to the power of lambda t. This by Markov inequality, this is e to the power of lambda x, expected value of e to the power of lambda x divided by e to the power of lambda t. That is, I am taking the denominator to the numerator. Now 17 is used. What is 17? The definition of a sub-exponential. Please understand, what is the theorem? The theorem says x is a sub-exponential random variable, sub-exponential random variable. So, with a sub-exponential random variable, this inequality comes into play. So, these are e to the power of lambda t, e to the power of lambda x, where since 17 is used, let us go back to 17 just to be able to get a feel for that. Random variable is said to be sub-exponential if expected value of e to the power of lambda x minus mu is less than or equal to 2 to the power of nu square lambda square by 2 for lambda less than or equal to 1 over b. That is exactly what we are applying in here. Yes, it is a bit involved, but we will soon see that it is very useful. So, you substitute these. Now, you can combine the two, you get g of lambda t. G of lambda t is nu square lambda square by 2 minus lambda t. So, and I am going to have to minimize this because it is an upper bound. So, this is a constraint minimization of g lambda t. This is a function of lambda and t, mu, the parameters given. So, it can be verified that the constraint minimum occurs at lambda star is equal to t by nu square for a fixed t, for any fixed t, that is the minimum. Therefore, for t lying in the range 0 to nu square by b, it is also a constraint minimum, because I show the interval is contained in that. Therefore, g star t, the optimal value, is minus t by 2 mu square. So, for t greater than mu square by b, g for a fixed t as a function of the first variable is monotonically decreasing in the interval 0 to lambda star, and the constraint minimum occurs at the boundary lambda star is equal to lambda plus is equal to 1 over b. Therefore, g star of t is equal to g of lambda plus t. Lambda plus t is 1 over b. So, t minus t by b plus nu square by 2b square, which is less than or equal to minus t by 2 alpha, where t is greater than or equal to nu square by b. So, these are involved calculations, but they are pretty straightforward. Note, as in the example in section 12 above, this is the 14th section in here, the sub-exponential property can be verified by explicitly computing or bounding the moment generating function. If this becomes difficult, an alternative is to control on the polynomial of the moments of x. So, we can approach by either computing the polynomial moments, polynomial e to the expected value of x minus mu to the power k, or manipulating the moment generating function. It is here the Bernstein condition comes into handy. So, what is Bernstein condition? Bernstein condition with the parameters with a parameter b holds if mu is equal to E of x, sigma square is equal to the variance, and the kth central moment, absolute value of the kth central moment is less than or equal to 1/2 of factorial k sigma square b to the power of k by 2. Look at that. These are bounds on the moments. This is called a random variable is set to satisfy the Bernstein condition with the parameter b if the mean is mu, variance is sigma square, the kth moment for k greater than or equal to 3, the absolute value of the absolute value of the expected value of the kth moment, which is upper bounded by factorial k b to the power of k minus 2 sigma square. So, under what condition this will be satisfied? This will be satisfied when x is bounded. So, Bernstein condition implied by when x is bounded, and we are going to be relating sub-exponential to Bernstein's condition. So, using this we can get a sharper tail bounds, and is applicable for unbounded random variables as well. Hence, its wide applicability, So, I want you to be able to keep track of all the things that we are doing. We talked about Hofding conditions, now we are talking about Bernstein's conditions. Bernstein condition essentially tells you the kth moment is finite, and he is simply not only finite, he gives an expression for the upper bound. So, what kind of random variables will satisfy these bounds when x is bounded? So, let x mu sigma square satisfy Bernstein condition. That means x is a random variable with mu mean and sigma square is the variance. Let this satisfy the Bernstein condition with the parameter b. Then expanding e to the power of lambda x minus mu, I get the expected value of that is equal to given by this infinite series. But we do know Bernstein condition bounds e of x minus mu to the power expected value of x minus mu to the power k. So, this is the bound on expected value of x minus mu to the power k, that is less than this. So, if you substitute that and simplify and require that the absolute value of lambda is 1 over b, then the right hand side, the sum of the geometric series gives e to the power of expected value of e to the power of lambda times x minus mu is less than or equal to 1 plus lambda square sigma square by 2 divided by 1 minus b times absolute value of lambda. This is less than e to the power of lambda square sigma square by 2 divided by 1 minus b absolute value of lambda, because 1 plus t is always less than e to the power of t. Hence, the expected value of e to the power of lambda x minus mu is less than or equal to e to the power of lambda square root of t. So, here I am trying to rewrite this as square root of 2 times sigma square divided by 2 when lambda is less than or equal to 1 over 2b. So, this becomes this under this condition. Note that sigma square lambda square divided by 2 times 1 minus b times modulus absolute value of lambda is less than or equal to lambda square sigma square by 2 times this quantity, which you can essentially show is lambda square root of 2 sigma square by 2. Therefore, x is a sub-exponential random variable with parameter nu is equal to square root of 2 times sigma and b replaced by 2b. So, look at this now. Bernstein type bound, it is all tail bounds. So, for any random variable satisfying Bernstein condition 20, we have the moment generating function is upper bounded by this quantity as for lambda less than or equal to 1 over b. This is a summary, and the tail bound is given by the probability that x minus mu is absolute value of x minus mu greater than or equal to t is less than or equal to 2 times e to the power of minus t square by 2 sigma square bt for all t greater than or equal to 0. 22 is proved as above, and using this we can get a bound on moment generating function, we can get a tail bound on 23, and that can be obtained by setting lambda is equal to t over bt plus sigma square that belongs to the interval 0 to 1 over b, that belongs to the interval 0 to 1 over b. And we apply this in the Chernow bound. So, lambda is the parameter that appears in Chernow bound, and I am going to replace it by b and sigma square, the parameters for this particular variable. This bound has to be substituted and simplified, and that simplification is not trivial, but is a good homework to attempt. Is a good homework to attempt. So, we have covered lots of results. Why do we do that? Because we want to be able to compute the tail probability. Tail probability is of interest in computing the concentration. Concentration is a phenomenon that happens in high dimension, concentration of distance, concentration of probability measure. So, concentration of probability measure and high dimensional data analytics are related to each other. Now, we are going to talk about a note on the applicability. The consequences for a bounded random variable. So, let us see whether what does this imply for a bounded random variable. To say a variable is bounded means x minus mu, the absolute value is less than or equal to b. So, you can readily see x lies between mu plus b and mu minus b. That is a bounded. So, using boundedness to show that it is sub-Gaussian with the parameter b and apply Hovding inequality in section 9. So, this is how we are going to apply these bounds in practice. The second applicability is we show that the boundedness of random variable satisfying Bernstein condition and above bound in section 15. I have divided this module into different subsections numbered 1 through increasing integers. So, this tail bound shows that for small t, x is sub-Gaussian with a parameter sigma as opposed to b that would arise in Hovding inequality. So, I am trying to talk about all the interrelations between these. Since sigma square is equal to the variance and the variance is less than b square, this bound is never worse than the random variable when the random variable takes large values, occasionally with small variance. Occasionally with a small variance. So, what does it mean? Here the random variable is such that its variance is bounded. If the variance is bounded means what? The random variable can still take large values, but with a very small probability, with a very small probability. So, the next one is called the closure property of sub-exponential. Sub-exponential property is preserved under addition of independent random variables, so the parameters that transform in a simple way. So, if xk is a sequence of n independent sub-exponential random variables with parameters gamma k, b k, with mu k is equal to e of xk as a mean, then the moment generating function for the sum e of expected value of e to the power of lambda times the sum of the differences between the random variable and its mean, they are independent. So, this exponential is simply the product of the expectation. The product of expectations by virtue of the fact that its SE is given by this when lambda is less than or equal to 1 over less than or equal to maximum of 1 over bk, where the independence of the sub-exponential random variables are used in here because of we are replacing joint density by the product density. So, what does this say? This says that if xk's are sub-exponential, their sum is also sub-exponential, with the parameter mu star b star, where b star is equal to maximum of bk over k, and nu star is is equal to square root of the sum of the squares of nu k's. Using the result in section 13, we get the tail bound again. So, for t in this region, for t in a small bounded region, it is sub-Gaussian. For t very large, it is sub-exponential. So, that is a summary of number of interesting concepts. Some of you may wonder why we do all the things. The why, the answer why is going to be answered. The question why is going to be answered very quickly, because by using sub-exponential property, we can indeed derive a number of interesting results that is of generic interest in big data analytics. So, in summary, what is that we have done? Gaussian distribution, its moment generating function, Markov inequality, Chebyshev inequality, Chernoff inequality, Redmarker random variable, symmetrization argument, from Gaussian to sub-Gaussian. Sub-Gaussian requires lambda, the parameters, to be over the real line. By restricting the value of the parameter to be a part of the real line around the origin, I can further extend the notion of sub-Gaussian to sub-exponential. So, these random variables are indirectly defined by their moment. If I can indirectly define by their moments, moment generating function, we can invoke the tail of the Chernoff bound to get the tail probability. So, you can see the role of Chernoff bound in all of these subsequent elaborations. So, in that context, we talked about Hovding random variables, Bernstein's condition. These are important results from probability theory. These are not generally dealt with in a standard course in probability theory. These are things that come from the interest that's stemming from large scale problems where the dimension d is very large, n is very large, d over n is alpha not equal to 0. So, we have seen chi-square variables. So, I am now coming to a concrete example. Let Zk be a set of IID random variables drawn from normal 0, 1. Here is where I am going to apply many of the results. Let y be the random variable which is the sum. This must be n, sorry. This must be n. And this is called chi-square. This random variable is said to be chi-square distributed. As in the example in section 12, y is sub-exponential with the parameters sigma and b, where sigma is equal to 2 times square root of n and b is equal to 4. So, we are trying to quote the results from the previous development. Why are we interested in this? Look at this now. Z is a vector with z1, z2, zn. We are going to be concerned with the square of the norm of that, which is the summation zk square I is equal to 1 to n. So, this variable is essentially the square of the norm of z. The square of the norm of z is chi-square distributed. So, what does it mean? If I have an n-dimensional space, if I am going to generate a random vector z, each of whose components are identically distributed from the standard Gaussian n 0, 1, and the Zn represents a point. What is the distance from the origin to that point? What is the square of the distance from origin to the point? So, that is what is being done in here. Now we have shown in section 2 that this variable is a sub-exponential variable with specific parameters. If it is a sub-exponential variable, it inherits a tail distribution. That is the reason why we did what we did. Therefore, I can get the first tail distribution result in here. So, what is that? The zk comes from normal 0, 1. So, zk square, expected value of zk square is 1. With me? Expected value of zk square is 1. So, each of the so what is this is the variance of zk square. So, I am considering zk square minus 1, it comes from this consideration. I am trying to compute the sum of the differences. I am trying to compute the sum of the differences. So, this is a random variable, this is the expected value, the difference between the random variable and the expected value summed over average, the absolute value of the average of that quantity is greater than or equal to t. And this is the tail distribution. Because this random variable zk square is SE with a parameter 2 times square root of n, comma 4, by applying the results in the previous section, it can be now shown for t in the interval 0 to 1, this tail probability is no more than 2 times e to the power of n t square by 8. Wow, that is a very interesting thing. So, as n goes, even though t is bounded, the probability goes to 0. That goes to show that this random variable is very highly concentrated for large n. Why this is highly concentrated for large n? Because the tail, the total tail probability on upper side and the lower side sum together is less than 2 to the power of e times minus n times t square by 8. So, n is the dimension that we are interested in. This has a very beautiful application in big data analytics, and that is called Johnson-Linden-Strauss embedding. And this is the reason why we did what we did. So, let us consider a set of n points, capital N points in d dimension. D is large. That means I have n objects in a d dimensional space, n points in a d dimensional space, and d is large. When d is large, it requires too much of space to be able to store it. So, what is that we want to do? We want to be able to compress it. We want to be able to seek, we seek a map from RD to RM. I am sorry, this is RD to Rn, n is less than, far less than d. So, I am going to map from larger dimension to smaller dimension, that is called the embedding. So, what is the condition on embedding? Please understand, capital N is the number of points, little n is the target dimension, capital D is the given dimension. I want to be able to represent a set of capital N points and map them from dimension D to dimension n. Now, I want to be able to tell you a particular theorem. So, if I have an equilateral triangle in 2D, ABC, the sides are 1. If I want to map an equilateral triangle into 1D, I can say A, I can say B, I can say C, I can preserve the distance from A to B1, C to A1, but I cannot preserve the distance between B and C to be 1. That means, I cannot embed a set of 3 points connected in an equilateral triangle and preserve the pairwise distances in trying to map the 3 points from 2D to 1D. So, what is this basic idea? The basic idea is that when you try to come from lower to higher, I have more degrees of freedom, so I can align myself very well. So, if I am going from lower to higher, the lower dimensional space is subspace of the original of the larger dimensional space, so I don't need to do anything. But when I am coming from higher to lower, I have restrictions. For example, it is very easy to move from a smaller house to bigger house, but it is very difficult to accommodate all the stuff you have from a bigger house to a smaller house when you scale down. The same idea in here. So, this aspect of being able to embed a triangle from 2D to 1D, while I can do ABC, I am able to preserve the distance AB, distance AC, but I am not able to preserve the distance BC. So, what is that to be for such mappings? So, I seek a map F which is from RD to Rn with n much far less than D, such that it preserves the essential features of the data. I want to store only f of u1, f of u2, f of un. See that these are images of the objects and each of them belong to Rn. One goal in trying to do that is that I want to be able to preserve the pairwise distances between F, just like the pairwise distances between A, B, C. So, if there exists a mapping where I can preserve the pairwise distances, it is called isometric mapping, isometry. Isothermal, constant temperature; isobaric, constant pressure; isometric means constant distance. So, if I can preserve the pairwise distances called isometric embedding, but this counterexample from 2D to 1D tells you isometric embedding in general is not possible. If isometric embedding is going to be difficult, what is that we do? We ask for the next best thing. So, the distance between ui and uj in the original space is square the norm of ui minus uj, 1 plus delta, this is 1 minus delta. If delta is small, this is slightly larger than the distance, this is slightly less than the distance. So, I want the distance to the images, the square of the distance between the images, f of ui minus f of uj, the norm of that. So, this is the vector, this is the vector, difference is the vector, the norm of that vector. This norm of the vector is computed in the n dimensional space. This norm of the vector is computed in the d dimensional space. So, if delta is very small, this is called near isometry. Near isometry. Please understand, we can only achieve a near isometry. So, equation 26 essentially tells you the distance between the images, the square of the distance between images is within a small fraction of delta of the distances between the original objects, the small distances between original objects. So, this is called near isometric embedding. So, the whole question is this: how do you achieve this? So, you can think of this as data compression. So, 24 is what is needed in data science. So, I have a collection of capital N points in the d dimensional space. I can't change the number of points, I have to map all of them to the n dimensional space. So, f of ui is the image of ui. I would like one possibility is to be able to preserve the pairwise distances. There could be other possibilities. If pairwise distances can be preserved, it is called isometric. We now know pairwise isometric is not possible. If something is not possible, we compromise. So, what is the compromise we are looking for? Near isometry. How near is near isometry? It is defined by the parameter delta. If delta is small, it is closer. If delta is slightly larger, the distances I am going to let them to be a little larger than that. So, if I can achieve this, Instead of storing ui, I can now store f of ui. There is a lot of savings in the storage space, and instead of processing ui, now I can process f of ui, and f of ui are smaller dimension. Therefore, I save in space and time by performing this mapping, this embedding. Johnson and Lyndon Strauss in the mid-80s showed that such a embedding is possible. There is a solution, there is a beautiful solution for this, and we are going to describe that solution process in the next class. Thank you.